In this chapter, we will be exploring the calculus of trigonometry. In this lesson, we will be introducing the fundamental trigonometric limit.
Okay, hi everybody. Now we're going to move over and we're going to start to talk about the calculus of trigonometry. And at this point, what I would sometimes do here is start the chapter by going over and reviewing some of the properties of the trigonometric functions, making sure students were comfortable with identities, with the unit circle, special triangles, and whatnot. But for right now, without going through that kind of a review, because I've got lessons for that out there, and I'm sure your teachers have gone over that as well. So I'm going to assume a certain level of comfort with this so that we can move right into it. And one of the first things we got to look at here is this fundamental trigonometric limit. Okay, because as soon as we start looking at brand new functions, we need to go back, particularly if we're going to do calculus, we got to go back to first principles, which means going back and talking about limits all over again. I know it's been a while since we've done this, but we need to do this. And in fact, when we get to the chapter on logarithms, which will come next here, we'll have to do the same thing. But before we get into the fundamental trigonometric limit, okay, and I'm going to prove this to you. I'm going to show you some interesting mathematics here. What we're going to do first of all is just go back and let's just talk about our two primary trig functions here. So let's take a look at y equals the sine of x, or sine of theta, sine of x here. Let's just take a look at what the graph looks like. Okay, so I'm going to give myself a little scale. So this is going to go up to 1, this will go down to -1. And I'm going to go up by, let's say, this will be pi over 3. What have I got here? Yeah, I'll go like just 2 pi over 3. Whoops. Pi, 4 pi over 3, 5 pi over 3, and then out here at 2 pi. Okay? So when I plot this here, I'm going to start here at my origin, and that's the way the sine function works, and it's going to go up. It's going to go up. What have I got here? Up, down, 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 center, there, 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 there. So the trig function is going to look something like that. Okay, well that's not too bad. I've done worse. Anyway, so there's a good graph of what the sine function looks like. Okay, y equals the sine of theta. And you should be comfortable with that. Now let's take a look at the cosine of theta. And we'll use the same scale here. Pi over 3, oops, 2 pi over 3, pi, 4 pi over 3, 5 pi over 3, and 2 pi. Now, we know that cosine starts at its apex, okay? And so it's going to go down, then it'll go down to the halfway mark, 0, halfway mark there. At pi, it's down at -1, halfway back up. So cosine is going to look like this. Okay, and I know this. Okay, that has looked better. But anyway, you get the idea. There's your sine of theta. Here's your cosine of theta. We're looking at single periods here. Now what we want to do is we want to just take a quick talk, have a quick talk about a couple of what should be fairly clear limits here. And to make this conversation make a little bit more sense, I'm just going to extend both of these functions just backwards a little bit. Okay, so there's my sine graph. My cosine graph is going to look something like this if I just take it back a little bit there. Okay, and so now with this in mind, I want to talk about what is the limit as theta approaches 0 of the sine of theta. So we're going to focus our attention right here. And so as you approach 0 from the left, take a look at what the points are doing here. Okay, look at all the points on the line. As you approach 0 from the left, the y-coordinate seems to be getting closer and closer and closer to 0. From the right, if they follow the function, all of those points get closer and closer and closer to 0. So it seems pretty clear that the limit as theta approaches 0 of the sine of theta is going to be 0. Now let's take a look here at the limit as theta approaches 0 of the cosine of theta. this case a little bit different. As you take a look at all of the points, this infinitude of points that lead up to where theta is equal to 0, all of those y-coordinates there, the values of the dependent variable getting closer and closer to 1. And that is true if you come at it from either the left or the right. And so the limit as theta approaches 0 of cosine is 1. Okay? And I'm just getting that based on those graphs there. Now, just for a moment, before we get into the actual fundamental trigonometric limit, we're going to take a moment here and just take a look at what a question might look like asking for the limits here. Okay, so here we go. We're just going to do this real quick. We're just going to take a look at an example of this. So let's say we're going to take the limit as theta approaches 0 of a function that looks like this, the cosine squared of theta minus theta plus 2. Okay, well, we know that this is going to equal to the limit as theta approaches 0. Oh, actually, I don't even know why I wrote that down. I don't even need to write that down. My mistake. Okay, because what I'll do here is I will just simply take the limit, because I can do that right now. I don't have to write this down. Actually, I can just take the limit, because I know that as theta goes to 0, cosine of theta is going to approach 1. So it's going to end up being 1 squared. I know that as theta approaches 0, sine of theta approaches 0, so I'm just going to replace that with 0. And then over here, I know that that 2, well, 2 is a constant, so it's not going to vary at all. It will stay constant at 2, so it's just going to stay 2 throughout this. And so, as I take the limit as theta goes to 0 here, I'm going to get 1 squared minus 0 plus 2, so I'm going to get an answer of 3. Okay, that's all we're doing. The point of this little example right here is really just to highlight that even though we're dealing with trigonometry, for the most part, what we're doing is no different than what you did way back when we started to work with limits initially. Basically, we're going to assume continuity, and we're just going to plug it in and look at the result. And remember, if I get a weird result like 0 over 0, okay, well then I have to consider something, okay? Let's take a look at another example. All right, so now in this case, I'm being asked to find the limit, and the limit is as theta approaches 0 of sine theta over theta. Now, if we try what I was just talking about here, if we substitute 0 in for theta, sine of theta is 0, and then theta just becomes 0. So this is actually going to become 0 over 0. Which, remember, that is an indeterminate form, which means I've got some work to do. So just like it was way back at the beginning of this course here, when you get an indeterminate form, you've got some work to do. Okay, now, thinking about what we used to do, if we had a radical in there, we would rationalize. If there were some fractions in there, we would add the fractions together. If there was some expression, or polynomial expression, or sometimes we could factor. We are kind of left looking at that wondering, what am I going to do? So just to start off with this, just to investigate what's going on here. And by the way, notice that sine of theta over theta, that is undefined at 0. Okay, we are looking for how this function here behaves close to 0, but we know that at 0 it is undefined. So we can state here that theta can't be equal to 0. But the limit doesn't care about that. The limit is only about the behavior of the function prior to and after that value. But without having a nice approach to this right now, let's do it the kind of the down and dirty way. Let's just get through it and let's evaluate the limit. So let's approach, let's find the limit as theta approaches 0. Let's go from the left first of all, of sine of theta over theta. And let's just take a look at a table of values. Okay, theta, sine of theta. And so we're going to approach 0. So let's make it like negative 0.1, negative 0.01, negative 0.001. And when we plug those things in, and I've already done this for us here, we're going to get 0.998334. And when you plug this in, you're going to get 0.9. Sorry, I copied that down. I meant 0.999 0.9983 repeating. And this is going to be 0.99999983 repeating. So I think you're getting a sense of where this is going. But just to be sure, let's go and let's take a look at what happens if we approach 0 from the right of sine theta over theta. Same thing. So theta, sine of theta. So we'll approach this as 0.1, positive 0.1, 0.01, 0.001. And there's a beautiful little bit of symmetry here. This is 0.998334. This is 0.99998, and I believe it's 3 repeating. 0.9999983 repeating. Okay, and so I hope you can see that what's happening here is these are both approaching the same value, and that value is 1. Okay? That's the value of that particular limit right here. Now, that is right there. This is the fundamental trigonometric limit. That is the limit that we want to spend, or that we are going to spend a good chunk of our time working with in this particular chapter here. Okay, now I'm going to draw this out for you. I'm going to explain this a little bit, but what I really want to do right now is I want to take a moment aside here before we get into applications of this, and maybe a little bit of a discussion of what we can do with this. I do actually want to give you a proof of why that particular theorem works, or why that particular limit is what it is. More than just this kind of brute force method of plugging in values. Okay, and by the way, we might as well take a quick look at it right here. If you were to graph this, what you would see is something that looks like this. Okay, the graph kind of dips below here, comes up to 1. It's not defined there, goes up like this, and keeps going. So graphically, you can see that it is, in fact, approaching 1 there. But there is this discontinuity here. Okay, there is a discontinuity up there. It is not defined, and we had said that before. It is not defined when theta is equal to 0. Anyway, now I want to take a moment, and I want to show you the proof of this. Okay, everybody, now I'm going to prove to you the fundamental trigonometric limit. And the reason I want to do this, show you more of a firmer proof than just what you're looking at when you look at a numerical demonstration here. I want you to see what you would see at a university here, okay, how they would approach this. And this requires that I introduce you to the sandwich theorem. Okay. And this states here that let's assume that g of x is less than or equal to f of x is less than or equal to h of x. Whoops, sorry, can't see that. Over some interval I. Okay? So just within this interval, and this interval could be all reals, but it doesn't really matter. As long as we've got some sort of interval here, and we know that for all values of x there, that g of x is going to be less than or equal to f of x, which is in turn less than or equal to h of x, okay? So that's the scenario we've got here. Now, we're going to look at, we're going to assume, okay, we're going to assume that c is an element of this interval here. Now, I'm going to create a limit here in just a second where I'm approaching c. And I want you to really pay attention to what I write here. It does make sense if you think about it, but sometimes when you just look at it, it's not clear. I will draw a picture though in just a second. So what we're going to say here is, let's assume that the limit as x approaches this c, okay, for g of x is exactly the same as the limit as x approaches c for h of x. And that limit is, I don't know, some number L. Doesn't really matter what it is, but they're the same. okay, then what that means is, therefore, we can conclude that the limit as x approaches c of f of x is also equal to L. That's the sandwich theorem. That's what it's saying. And basically, graphically, if you want to think of what's going on here, what it's saying here is, let's say you've got some sort of interval, okay, and in that interval you've got the g function, and then you've got the h function. Okay, we've established that for some value c, okay, let's label these. This is g, this is h here. Okay, so we've got our interval I here. C is within that interval. And that at some point here, the two functions have the same limit. Okay? So they're approaching the same value here. Now, if it's true, and maybe I'll use a red pen here. If it's true that the f function is always greater than or equal to g, and always less than or equal to h in this interval, then f doesn't really matter what f is doing. If that statement is true, then it has to be equal to those two at that same limit. Basically, just like the theorem, the name of the theorem states, these two functions sandwich that third function in between them, and so they all meet at that one point. That is all the sandwich theorem is stating. Okay? So with that in mind, let's now take a look at our trigonometric limit here. And what I'm going to do to establish this, okay, is I'm going to draw a picture. So I'm going to draw a picture here, and let's say it looks something like this. Let's say that this is part of a unit circle. So this up here is the point 0, 1, and this down here is going to be the point 1, 0. Okay? So here's our origin. Now, what I'm going to do here is I'm actually going to create a handful of shapes here, and we're going to talk about the relationship between those shapes here. So bear in mind, though, that what I've drawn here is a quarter of the unit circle. Okay, so that's significant. Okay, so I'm going to draw a line here. Actually, I'm going to draw it kind of way out here. There's a reason why I'm extending it like that. I'll get to it in just a second here. Now, I'm going to take this point right here, and let's just call that point P. Okay, and it's going to have coordinates here, x, comma y. But remember that y coordinate in this case is going to be the sine of theta. Okay, and now I'm going to connect that. Let's call this over here point A. Why not? So I've got this triangle right here, OAP. So the area, okay, of triangle, or OPA or whatever, okay, the area of that triangle is going to be 1/2 base times height. Okay, so it's going to be 1/2. The base here is just going to be 1. And the height here, okay, bear in mind that's going to be the y coordinate. And because this is on the unit circle, okay, that is going to be the sine of theta. Because remember, the x and the y coordinates here, the x coordinate is the cosine of theta. Okay, the y coordinate is the sine of theta. So basically, the area of this triangle right there is going to be 1/2 sine theta. Okay, that's a good start. Now, the other part of this that I want to draw your attention to is I want to take a look at the area, and maybe come over here, the area of sector. Now, how am I going to label that here? Well, let's just call it the area of the sector, because I really only got the one sector here. So it's this bit right here. It's basically the triangle with that little bit of a curved piece to it, okay? That segment right there. So we're going to take the area of that sector, and because we're talking about this in terms of radians, okay, the area of that sector is going to equal 1/2 theta r squared. But in this particular case here, I've already established that the radius here is just 1. So this is actually going to be just 1/2 of theta. That is the area of that sector. Now notice the relationship here. The area of the sector is always going to be slightly bigger than the area of that triangle, no matter what angle we choose. Okay, excuse me, sorry, in the interval here, a little bit less than pi over 2 down to 0. It's always going to be like that. Now let's build another triangle here, and this time what I'm going to do is I'm just going to come straight up. Okay, we're going to meet up here. This point right here, okay, this point, let's call this B, for lack of a better letter here. This is going to be the point 1, comma, okay, well, how high up does that go? And I hope it doesn't take you too long to realize here that, bear in mind that how do these two sides relate here? Well, that's a tangent here, okay? The tangent is the opposite side over the adjacent side. But in this case here, the adjacent side here is just going to be 1. So this is actually going to be 1 comma the tangent of theta. And so now if we take a look at this, the area of triangle OAB is going to be 1/2 the base, which in this case again is 1, multiplied by the tangent of theta, or 1/2 tangent of theta. And that triangle, okay, for all these kind of angles that I can draw here, that triangle will be bigger than the sector, which is bigger than that smaller triangle right here. So now let's write that out here. So this is what I've got. I've got 1/2 sine of theta is going to be less than 1/2 theta, the sector, which is going to be less than 1/2 the tangent of theta. Okay. Now, because I have a very specific goal in mind here, I'm going to do something kind of nice to this. What I'm going to do is I'm going to divide everything through here by the sine of theta. Now, normally I'd have to really pay attention to that, because if you multiply or divide by a negative, it's going to change the direction of the signs. But in this case here, because of the interval that I'm choosing to look at here, I don't need to worry about that. Okay, all of my sine values here are going to be positive. So I'm going to divide by the sine of theta. Actually, I'm going to divide by 1/2 too. In fact, I could probably just divide by 1/2, multiply by 2. I could probably just do that right away here. Get rid of that. Every one of those has the half in it, so I don't really need that. Now I'm going to divide everything through here by sine, and that is going to get me 1 is less than theta over the sine of theta is less than the cosine of theta. Oh, sorry. 1 over the cosine of theta. I do know what tangent is. 1 over the cosine of theta. Sorry, I knew where I was going to. That didn't look right. Okay, that's fantastic, because now I see that expression that I'm interested in. Now what I'm going to do is I'm going to reciprocate everything. Okay, but bear in mind, if you reciprocate a small number, you get a large number. If you reciprocate a large number, you're going to get a small number. So basically the order here switches, and so when I reciprocate that, it's going to look like this. And remember that when I take the limit, recall that the limit as theta approaches 0 of the cosine of theta is going to equal 1. So if I now take the limit as theta goes to 0 here, this goes to 1, my constant function is always going to be 1, so it won't change. And I had already established that this is always going to be, initially I established that it was going to be greater than or equal to this function, less than or equal to this function, then I reciprocated it, so the order kind of switched here. But this one's always going to be in between. So therefore, by the sandwich theorem, okay, the limit as theta approaches 0 of the sine of theta over theta must equal 1. Okay. Again, I just wanted to take a moment here, kind of show you what more of a formal proof would look like, okay, and not just the number plugging. So anyway, let's keep looking at the fundamental trigonometric limit. Okay. Now, before I start to do some questions with you, using the fundamental trigonometric limit, a couple of things I want to comment on. Just first of all, the reciprocal is also true. Okay, so the reciprocal is true, meaning that the limit as theta approaches 0 of theta over the sine of theta is also equal to 1. And actually, at one point in our proof, we actually had the reciprocal trig function there, and had we taken the limit at that point right there, we would have seen that result as well. So in either case there, the reciprocal is true. Here's an idea though, and man, I cannot overstate the importance of this next relationship here. That the fundamental trigonometric limit implies, okay, it implies that the limit as theta approaches 0 of the sine of theta is theta. Okay, now just think about it for just a quick second here. We can go back up to our reciprocal here for a second. If this is becoming 1, then these two must be getting closer and closer and closer to each other. Okay, where the limiting behavior of this is that they are the same. That's why the limit becomes 1. Now, you can actually see that if you go to your calculator and start to take the sine. Now, please make sure you're in radian mode, okay? You should, in fact, I should have stated this right off the bat here. In all of calculus here, we're in radian mode. We don't typically use degrees at all. So you plug in some really small values of theta and take the sine of theta. You'll notice that that angle, the sine of the angle, is actually very, very close to the angle itself. That is an idea that actually gets used in physics. Okay, you'll see that used in optics here. Because what this means is that, therefore, for small values of theta, and it has to be really small values of theta, okay, sine theta and theta are interchangeable. Okay, and actually, like I said, you will see this in physics, in optics here when we're talking about diffraction gratings. Okay, by replacing the sine of theta with a theta, you actually make some of the equations very, very straightforward. Okay, it simplifies them quite a bit actually. And you're allowed to do that because in those particular situations here, the angles that you're talking about are quite small. Now, similarly, one of the reasons why I think this is so valuable here is because when you do this, okay, when you recognize that theta is getting small, okay, that causes these two to be interchangeable, what that does is it actually demonstrates kind of a deep understanding of what calculus is trying to talk about here. Let me go back and show you this. Let's take a quick look at our graph, okay, of the trig function here. And let's go up by let's say that this was pi over 3. This is going to be 2 pi over 3. Let's say here's my 1, so I'm going to go up to there. Pi over 3 will be there, and this will be right there. And then I'll just go back negative pi over 3. Negative 2 pi over 3. Okay, so and this is my negative 1. So right here, I'm going to try to draw this as cleanly as I can. Okay. Basically what this is saying, and I'll use red here, that if you were to draw out, and bear in mind my scale is a little bit wonky here because I took 3 steps here up from 0, 3 steps down to get to 1. This is pi over 3. So anyway, my scale is a little bit wonky. My graph's a little bit stretched out a bit here. But if you were to graph y equals x, so let's do this. This is y equals the sine of x. If you were to graph y equals x, oh no. Okay, this is y equals x. What's significant here is as you get closer and closer and closer to 0, these two functions, here we go, behave the same. Okay, that curved sine function, when you zoom in, Okay, now I can't go too far here. When you zoom in, but when you get really, really close here, sine behaves like the straight line y equals x, very, very close to the origin. And isn't that what calculus is saying all the time? Every time you take a derivative, okay, every time you take a derivative, you're finding the slope of the tangent line. Because what you're saying is, over here, let's say, that right here, the behavior of the graph at that point, if you zoom in on it, is very, very close to the behavior of this very specific tangent line. Okay, so when theta is small, okay, when theta is small, when theta approaches 0, sine theta and theta become interchangeable. And then the last point here that I want to bring up here, and this is really just an extension of this idea, but one that I want you to be familiar with here, is that since the tangent of theta is the ratio of the sine of theta over the cosine of theta, and bear in mind that the limit as theta approaches 0 of the cosine of theta is 1. We looked at that initially here, okay? And we need to know that. What this means is, therefore, when theta is small, or let's say close to 0, tan theta and sine theta behave the same. Okay? When theta gets really, really small, cosine theta is going to go to 1, which basically means for really, really small values of theta, tan theta and sine theta act the same way. So therefore, the limit as theta approaches 0 of the tangent of theta over theta is also going to approach 1. Okay? Now, and that means that the limit, as theta approaches 0 of the tangent of theta is also equal to theta when theta gets really small. Now, again, meaning that they can be used interchangeably. Now, again, just to illustrate what is going on here, let's take another quick look at the graph. Okay, so, and if I go up again by pi over 3, 2 pi over 3, negative pi over 3, negative 2 pi over 3, let's call this 1, negative 1. So here we go. Sine starts at 0, okay, halfway there, almost there, there's pi over 2, halfway there, almost there, there's negative pi over 2, so here's sine. Okay, now, here's the graph, y equals x. Okay, but here is tangent. Remember, tangent is going to have this asymptote here at pi over 2 and at negative pi over 2. And what tangent does is tangent kind of behaves like this. It's going to come screaming up here, crosses over, and then goes screaming up here. Now it's a little bit tighter here, but then it's going to approach the asymptote as we go along here. So tangent kind of stays down here, comes up, does the little curve in, passes through the line y equals x, and then curves up here. But right here at the center, once again, all three of those graphs line up beautifully and behave very, very similarly, very, very close to 0. Okay, enough of that. Let me show you what it looks like when you are asked questions where you have to apply the fundamental trigonometric limit. Okay, so let's take a quick look at some questions here. Let's say that I'm asking you to find the limit as theta approaches 0 of the sine of 2 theta over theta. Now, don't be too quick to jump to conclusions here, okay? Bear in mind that the fundamental trigonometric limit looks like this. It's the limit as, let's say, a approaches 0 of the sine of a over a. The argument of the trig function and the denominator here are exactly the same. And when that's true, and they're both approaching 0, then the limit becomes 1. But here they're not the same. The argument of the trig function is 2 theta, and the denominator here is 2. Okay? So oh, sorry, the denominator here is theta here. So one of the things that we can do here, and I'm actually going to show you like 3 different methods of doing this, and that's probably not even all of them, okay? But method 1 here, let me show you one way of approaching this. One way to do this is to apply an identity. So the limit as theta approaches 0 of the sine of 2 theta over theta is going to equal the limit as theta approaches 0 of 2 sine theta cosine theta over theta. Okay. Now, when we do that, okay, what we've got here, 2 is just a constant multiple here. That's not going to be affected by the limit, so it's just going to be 2. Then we've got the sine of theta over theta, and when you put that together, we already know that as theta goes to 0, that's going to go to 1. And then the cosine of theta, all on its own, goes to 1. It doesn't really care as we get close to 0. And so then the product of those 3 is just going to be 2. So the limit as theta approaches 0 of sine of 2 theta over theta is just 2. Let's look at another way of approaching this. So once again, we're looking at here the limit as theta approaches 0 of the sine of 2 theta over theta. Now, actually, maybe what I'll do here is I'll show you one method here, but maybe 2 different ways of executing it. One thing that you might do here, and I'll use a different color just so you can see this, I've got the sine of 2 theta over theta. Maybe what I want to do here is, because I know that the argument has to be identical to the denominator, maybe what I do in this case is I'm actually going to put a 2 down there next to the theta. So that now they are exactly the same. But if you do that, you know that you can't just randomly change the denominator. I actually have to come up here and change the numerator, right? I have to multiply numerator and denominator by the same value in order to make sure that those are the same. But now I've got that this sine of 2 theta over 2 theta is going to go to 1. So I'm left with 2 multiplied by 1, or once again I get an answer of 2. Now, the other way of looking at that, and this is exactly the same method, it's just, again, another way of executing it. I might look at this and say, okay, my problem here is this 2 theta, that is the argument of that trig function. So I'm just going to slide over here a little bit. I'm going to let x equal 2 theta. Basically, I'm going to create what we call a dummy variable, which is just going to let me to manipulate this expression just a little bit so that I can do the limit here. So, and if x is equal to 2 theta, x over 2 is going to equal theta. And so now I can come back here and I can rewrite this. Okay, and notice in this case now that originally I'm letting theta go to 0, but just look at my expression here. If theta goes to 0, then so does x. So really, I'm letting x now go to 0. This is now going to be the sine of x, because 2 theta is x here. And the theta down here, we just figured out was x over 2. So this is now the limit as x approaches 0. I'm going to deal with this division by a fraction, so this becomes 2 sine of x over x. Sine of x over x goes to 1, multiplied by 2, once again, is just 2. Now, one more method. Okay, and I realize that sometimes showing people multiple methods here, it gets a little frustrating. You're like, just show me one method that works and away I go here. The problem is, and the reason why I feel obliged to do this is because I think some of you, your teachers are going to be expecting you to do different things here. Okay, so I just want you to have options here. But another method that you might employ is this, and this is actually my favorite. And although it sort of does look like a wee bit of a cheat, actually it's not. Okay, actually it's not here. What we're going to do is we're going to take advantage of what the fundamental trigonometric limit is saying about the behavior of the trig function. We know that as the argument approaches 0, the sign of the function starts to behave like its argument. So as theta goes to 0, sine of 2 theta is going to behave very similarly to just 2 theta. So I'm going to do a substitution. Now, although that looks pretty awkward here, again, I can do it because I'm letting the angle get really, really small. And now, theta divided by theta is 1. So now we've got the limit as theta approaches 0 of just the number 2, which is a constant. So there it is once again, the answer 2 pops out. Anyway, there's you've got like 3-ish methods of approaching the exact same limit. Let's take a look at a couple more. Okay, now for this question, we're being asked to find the limit as x approaches 0 of the tangent of 3x over 2x. And once again, I'm going to show you a couple different methods for doing this. So method 1 is again going to be to use an identity. Okay. Now this time I'm not going to do this a bunch of different ways. Just going to do this 2 different ways here. Most of the time, I suspect your teachers are going to require you to pull out an identity here. Okay? So I'm going to replace the tangent of 3x with the sine of 3x divided by the cosine of 3x, because tangent is sine divided by cosine. Okay? Now, and I'm thrilled with that right now, because cosine, as x goes to 0, 3x is going to go to 0. The cosine of 0 is just 1. So I'm totally fine with that being in the denominator, not a problem. But now I've got this sine of 3x over a 2x. Now, because the argument here is not identical to the argument down here, what I'm going to do is, and I could either do a substitution here and say, like, let's say theta is equal to 3x, or I could just multiply the denominator through by 3. Okay? So introduce a factor of 3 in the denominator, but I have to do it up to the numerator as well here. Now, just to make sure that you understand what I'm doing here, now what I've got is 3 sine of 3x over, bear in mind, order does not matter with multiplication. Sometimes when you get really far into your mathematics, sometimes it's those basic rules that we forget, that we do weird things with. So I can change the order here, make this 2 times 3x cosine of 3x. And so now, when I apply the limit, okay, the sine of 3x over 3x, that little bit right there is going to go to 1. The cosine of 3x, because the argument is going to 0, is going to go to 1. And so I'm left with just 3 over 2. Okay? So there's one method of doing this. Now, my method 2, and I'm just going to put it over here. My method 2, I think, is a little bit more direct here. So bear in mind, I'm starting with the limit as x approaches 0 of the tangent of 3x divided by 2x. Well, this is going to be equal to the limit as x approaches 0. Now, here's what we do here. Just like we said a few minutes ago, when x gets really small, when the argument of sine and tangent, when their arguments get really, really small, the behavior of the function is very, very similar to the behavior of the argument. So I can replace tan of 3x with 3x. So the limiting behavior of the tangent of 3x will be identical to the limiting behavior of 3x. The x's will cancel. We're left with the limit as x approaches 0 of 3 over 2, which is just a constant, 3 over 2. And so there it is again. Isn't that interesting? I love that. Okay, so in this question we're going to take the limit as x approaches pi of the sine of x over 1 minus x over pi. Now notice that we are not approaching 0 here. But if you plug in pi into the numerator and denominator, you're going to get 0 over 0. So you are going to get an indeterminate form. Now, there's no radical here to rationalize. There's no fractions to add or subtract. There's no polynomial to factor here. So what I got to do here is try to pull out the fundamental trigonometric limit here. And to do that, I'm going to change the function a little bit here. and I'm going to let my attention kind of get drawn to this. I don't want it to be x approaching pi. What I want it is for it to be x approaching 0, or the variable to be approaching 0. But notice what happens. If x approaches pi, then x minus pi must be approaching 0. Okay, now just think about that. Okay, and you'll see that that's true here. Now, what I'm going to do with this right here is I'm going to call h x minus pi. I'm basically just going to give this a variable name. And then to help me do a substitution, I'm going to bring that pi over so that h plus pi is equal to x. And I'm going to change the variable here. Just like I did a few minutes ago, I'm introducing this dummy variable h to change the expression here. So now this will be equal to the limit as h approaches 0. This will be the sine of, well, what was x? X is h plus pi. And then down here, I've got that x again, x minus h plus pi over pi. Now, I am going to show you two different methods of handling this particular problem here, but both of the methods rely on this as our starting point. Okay, so now I'm going to show you method 1 here, and then I'll come back to this step right here. But in both cases here, because I'm not approaching 0, I need to essentially transform the function or transform the limit so that I'm on 0 here. Now, there is another method I will show you at a later time in a later lesson here, where I take a different approach to a very similar problem, or actually I might even do the same problem there for that. But for right now, this is our starting point here. So in this method right here, what I'm going to do is I'm going to apply the sum and difference identity. So the numerator becomes the sine of h cosine of pi plus the sine of pi cosine of h all over. And I'm going to distribute the pi and the negative through. So this will become 1 minus h over pi minus pi over pi. Okay? This is going to be equal to the limit as h approaches 0. Now, watch what I can do here, because actually this thing cleans up very quickly, because the sine of pi is just 0. The cosine of pi is negative 1. So this becomes the negative sine of h. Pi over pi is 1, that negative there, so 1 minus 1 is 0, and I'm left with negative h over pi. So that very quickly became something a lot smaller and a lot easier to work with. This will now be the limit as h approaches 0. The negatives are going to cancel, and I'm going to multiply by the reciprocal of the denominator, so pi sine of h over pi, and now I've got this sine of h over h. I know that that's going to go to 1, and that leaves me with pi. There's my limit. Now, let me show you another method. Oops, method 2 here. And I will go back and rewrite the expression where I'm starting from there. Sine of h plus pi over 1, well, I'll just leave it like this. H plus pi over pi. We'll go right back to that. Okay, there is a bit of another identity that we can use instead of the sum and difference identities. And watch what happens here. Let's take a look at the circle. Sine of h plus pi. Let's just say h is out here. Let's say that this is my h angle. If you add pi to that, that's going to put you in quadrant 3. Still got a reference angle of h. But because this is in quadrant 3, that's going to be the negative sine of h. And you know what? No matter where that h is, if you add pi to it, just think about wherever you can put your angle h, if you add pi to it, it puts you in a quadrant where the sign changes. Even if you start down here, let's say you start in the 3rd quadrant. Okay, sine of that angle is negative, but if you add pi to it, it puts you up in quadrant 1. The sign is going to be positive. It's going to change signs here. So there's actually a little relationship here that we can use. Okay, it turns out that the sine of pi plus h is going to equal the negative sine of h. That's the rule we're going to use here. So this becomes very quickly the negative sine of h all over. And I just saw from the previous work here that the denominator is going to quickly become negative h over pi, which becomes the limit as h approaches 0 of positive pi sine h over h, just like before it goes to pi. So really what I'm doing here is I can avoid the sum and difference identity if I just have a sense of how that unit circle behaves, okay, when I transform that function pi units over. Anyway, there you go. There's some, well, a brief introduction, if we can say that, to the trigonometric, the fundamental trigonometric limit. I hope that makes sense, and I hope that helps you kind of get your first foothold into the calculus of trigonometry.